Hello, I'm going to work example 15.4 for y'all. In this example, we have two train cars both moving towards each other. One has a velocity of a positive 1.5 meters per second. We're going to call that to the right. And the other has a negative velocity of 0.75 meters per second. We'll call that to the left. And we're given their respective masses. One's 15 times 10 to the third megagrams, the other is 12 times 10 to the third, sorry, not megagrams, kilograms. Okay, and they want to know if they have these initial conditions right here, what happens after they couple? And by couple, they mean this thing over here. The trains, when they stick together, have basically a little handshake, and then they connect and move on together. So when they hit, since they have different velocities and different masses, they're going to move off together with one velocity, and we'll be able to figure out what that velocity or speed is. We're looking in just the x direction, so we can ignore vector signs at the moment, but I'm going to conserve momentum. Alright, we're going to find the speed after coupling, or after they stick. And so this is a system. Take note of that. We have mass A times the velocity of A initial. That's the momentum it begins with. Mass B times the velocity of B initial. That's the momentum of train car B. And then it's going to have some MAVA final plus some MBVB final. And when they say that it couples or that they stick, that means we can combine the masses, MA plus MB, and they will move off with some united final velocity. We still need to hold on to both of these terms though on the left hand side, because we know it has an initial velocity for each car. We know everything to find the velocity now. We know its masses. We know the initial velocities of the cars. We can solve for the final velocity as mass A V A initial plus mass B V B initial, all divided by the combined mass. And if you crank that out in your calculator, they will move off together to the right with a positive 0.5 meters per second. Alright, so we can also conserve momentum in the x and y directions on these problems. Let's take a look at what we can figure out if we do so. If I do impulse momentum, actually, let's look on A and see what happens. We can probably figure out what the force at the couple is, because if we use L1 plus the summation of the impulses applied, it's going to give us our L2. So on A, let's go ahead, look at only the x and y, the x direction. It's the only direction we have motion in at the moment. So we have its initial momentum as a 1500 kilograms, and I'm putting numbers in because we did come up with a number for our velocity. It had initial velocity of a positive 1.5 meters per second, and that would be our velocity of A initial. Some impulse is applied, It's going to be a negative force, and they told us what's the force if the impulse was applied for 8 seconds. And that's going to give our 1500 kilogram mass some new velocity, and we figured out what that new velocity is already. A positive 0.5 meters per second. Alright, we can now solve for F. We could also have done this by looking at B. If we looked at B, we would have the 1200 kilogram mass. They told us it was initially going 0.75 meters per second. In this case, we would have a positive impulse applied to it. It was going to the left, which we called negative, but a positive force to the right was applied for 0.8 seconds. And that's going to give us our 1200, sorry, that's 12,000 on all of them, and 15,000 kilogram mass, the same velocity, because they move off together. So this thing and this thing are the same. And we can also calculate F in the same exact manner. Alright, so we just found F. F ends up, sorry, to calculate real quick, is 18.8 kilonewtons. Alright, thank you for listening.